Hello. You probably scanned a QR code to come to this presentation. My name is Sawyer Bruzza-Oman, and this is my audio guided presentation of the Great Adventures of Food Chemistry, and this is the Rice Expedition. We're doing this because we want to look at the nutrient levels between foods grown in these different methods. And these different methods are conventional, which is monocropping, and it's the most traditional method that we are aware of at this time, using pesticides and herbicides and such. Organic farming is another one that we wanted to compare it to, and that's trying to avoid using those pesticides and herbicides and maybe trying to have a little more biodiversity. And then the third thing that we want to compare is regenerative ag systems. And it's a little more holistic and with the aims of trying to improve soil health in total. At the end, there's a lot of biodiversity in introducing of livestock to the systems. Be more specific, we are interested in phenols or polyphenols within these foods that are grown in these different systems. Um, Polyphenols tend to act like antioxidants, and they can reduce radicals that are caused from UV damage or from other pathogens within the body. Uh, Here on my slide, I have circled the phenol. A phenol is a benzene ring with an alcohol unit. The OH unit is an alcohol. And a polyphenol would be multiple of these within the structure. The third or the first structure are actually the polyphenols. Knowing the behavior of individual polyphenols is important, or knowing, what foods have these individual polyphenols is important because they can affect diets or medications or health issues that people have. So, for instance, grapefruit has some polyphenols in it that interact with some drugs like chemo or some antipsychotic drugs or some heart medication, and it can actually has influence on the amount of the medication that is uptook within your body. So it could be less or more, and that's kind of a problem. People who are anemic, they need iron, right? Anemia is a lack of iron. And some polyphenols in some foods can behave with iron within the gut, and they can bind to it, and they can actually prevent the person eating the food from being able to uptake that iron and actually making their anemia worse. Other things, chocolate actually has some beneficial polyphenols. If you're eating chocolate that is 70% cacao or higher, it can actually help reduce the inflammation within your veins in your body or other blood vessels. It's actually pretty good. So eating chocolate's a good thing. So polyphenols come in four different classes. Flavonoids is the most studied class. They've discovered, I think, around 4,000 compounds that fit into flavonoids. Thus, there are six subcategories within flavonoids. They all share this structure. As you can see in the image in the center, there's an A, B, C structure. So they all share that, but the different subcategories have different R groups coming off of that, which are different, have different behaviors and can lead to different structures. Flavonoids are found in most fruits and vegetables, and they influence the colors. They tend to be the ones that are responsible for that. Phenolic acids here are the next most studied class. They come from these benzoic and cinnamic acids as their base units, and they just have a phenol or an alcohol unit attached to them, and that ends up turning them into a phenol. So here, this ferulic acid on the screen, it's in a lot of anti-aging facial lotions. So it tends to have some anti-aging effects. It's usually found in your coffees and teas and some cereals. And now we're starting to get into the two classes that are less studied. So lignans, that's two cinnamic acid molecules that come together, and they're found in flax seeds and some sesame seeds. This is an example of one. This is laraceresinol. It's a type of phytoestrogen. And what this actually does within the body is it behaves like an estrogen. And this can actually be beneficial for people going through menopause. It can reduce the intensity of the hot flashes, and it can reduce some of the bone pain that can happen in menopause. Um, it's found in a lot of soy products. So a lot of Eastern countries that eat a lot of soy tend to have, less intense menopausal uh, behaviors, and it's been associated with this secoisolyriceresinol uh, that's in the soy products that they eat a lot of. Like miso soup has a lot of this in it. And so the fourth class of polyphenols are stilbenes. They're not really that popular within the foods that we tend to eat, but they're most popular in grapes. So something fun I like to think about for these stilbenes is this thing called a French paradox. So the French paradox, uh, people in France, they tend to eat a lot of fatty foods, rich fatty foods, and cigarette smoking is a pretty popular thing there. Uh, but amazingly, they don't have a lot of heart disease. And some people have started to associate this resveratrol to that French paradox because it's in wine. It's found abundantly in wine. And that, as we know, is also consumed frequently in France. So, yeah, it's kind of, if you can keep up on your resveratrol, maybe you can help prevent yourself from heart issues in the future. So today in the industry, ag industry and food industries, they tend to use assays to find the total polyphenol content in the food sources that they're studying. And I found in a lot of literature that many use gallic acid as a calibration curve, and then you can compare what you're studying to the calibration curve and determine the concentration within your sample. Uh, we think that's great because it works for them in their applications, but as chemists, and we're curious, we just kind of want to discover individual polyphenols and approach that way because we want to find if there's any associated benefits with individual polyphenols. So, extracting the polyphenols from the rice that I was doing this summer, these are two methods of approach that we have. The one here on the left, the CSUC method, that was provided by the ag department, and it works. It's great. But we also found a method in some literature that we wanted to try, and it's a little bit quicker. There's only centrifuging. We don't actually put it on the shaker or the sonicator, and that saves us some time. So we actually ended up using this curry method more often than the CSUC method. And as you can see later on in the slides, we'll start to see a little bit of a difference between the two. And yeah, so we ended up not using the CSUC method for the latter half of the summer. So once we got those extractions, we'd bring them over to Donna, and this is Donna. She's our one of our high performance liquid chromatography machines at Chico State. She's great. What we used with her was a reverse phase setup. So we had a nonpolar stationary phase, a nonpolar column, in which the compound went through, and it was pushed through with a polar mobile phase. And so what happens is we have our compounds with different amounts of, um, you know, intermolecular forces, and as they make their way through the column, they spend different amounts of time in the mobile phase and the stationary phase interacting with their, um, you know, functional groups and their intermolecular forces, and that's what dictates when they come out. So they end up coming out in different times, and we visualize that via the UV vis that Dawn is also equipped with, and that's how we get this spectra with different spikes in it. Initially in the summer, we didn't really have any any idea of what what column we were gonna use, what mobile phase we were gonna use. So we ended up having to figure it out experimentally. So we took a few different columns and we ran just the two extraction methods through them, and we compared them to see which ones we liked and which ones we wanted to take forward to the next test. So here we started with the columns. As you can see, there's the C4, C18, and then XB-C18. And the C4, it refers to the amount of carbons within the column. So inside the column, the stationary phase, there's 4 carbons attached to a silica. And then for C18, there'd be 18 carbons. And you can kind of visualize it like a spider web or like a lattice that this compound is being pushed through with different length carbon chains, depending on the column. And so what we ended up taking from this was the bottom 2. We ended up bringing them forward for further testing, and that was the mobile phase. So here we started doing the mixed acidic method. It was something that we found in a literature search, and it's kind of a nasty combination. Here we have 35% of 4% this, and 65% of 0.4% volume for volume of this. It's kind of, gross looking. But as you can tell, it did actually start to pull those peaks apart in that last slide. That is all multiple compounds. And as we start to change the mobile phase, you can see those compounds starting to separate, which is pretty cool. So then the next component of DANA that we can approach is the flow rate. So we can adjust the flow rate, and that can actually play a role in eluting these compounds through the system. So as you can see on the left, we have the fastest or the quickest flow rate, and on the right, we have the slowest flow rate. And as you can see, as you go from left to right, these compounds really do start to separate. On the bottom there, that spike in the beginning is some carryover from a previous slide or a previous run, I believe. So we kept reading literature sources because we kept trying to figure out, how to separate these bumps, and we came across another mobile phase that we wanted to try. This one uses water and acetonitrile. So what we did is we set up this really long sequence of runs where the first one was 100% water that the compound was pushed through, mobile phase, and the last one was 100% acetonitrile that was the mobile phase. And as we go through, we change it by 10%. And what we ended up really valuing or liking out of this one was the 70-30. So we ended up keeping that one and using that one further in the future. We ended up doing it with brown rice as well. I just wanted to show that 70-30 here is also the one that we like the best. While we were doing that, there was a couple issues. We ended up having to run that multiple times. As you can see, if your spectra starts with a really high absorbance unit, that's not good. It's not a good reading. So I just wanted to show some mistakes that were made along the way or found along the way. Basically, what we did after we ran these extractions through DANA, we then brought them over to ester. So ester is a GC, a gas chromatography. It's very similar to DANA, in which we have a stationary phase and a mobile phase. The difference this time is that the mobile phase is a gas. This molecule right here is what the stationary phase has inside of it. So instead of it being like chains of carbon, this is a siloxane that coats the inside, and it interacts with the intermolecular forces of the compounds, and then depending on heat is when the compounds leave. So that's how you get different retention times. As this thing ramps up in heat, the compounds leave at different times based on their boiling point. It's pretty cool. So what I ended up doing at one point was throughout the research was collecting the different humps after I slowed the flow rate down on DANA. I collected the different humps, and then I brought them over and tried to identify them with a mass spec, which Esther is equipped to. And a mass spec is basically a machine that breaks your compound into fragments, and depending on that fragment pattern, it matches it up to a compound, and that's generally it's like a fingerprint, so that's generally the compound that you're interested in. So we were using this to try to discover what exactly the polyphenols were within the rice that I was studying. So those attempts at collecting the peaks that didn't work with the GCMS. So I ended up speaking with a couple organic chemists that I was working next to, and they suggested a couple different methods of trying to silolate the compound. And essentially what that's doing is it's replacing the oxygen with a silicon. And what that does is it prevents the molecule from being able to salt out and not volatilize within the GCMS. And basically, what that means is that it'll force it to be in the correct state for the GCMS to read it, right? It'll make sure that it turns into a gas so that the mass spec can determine what it is. Unfortunately, I was still coming into some issues while doing that, and so we ended up having to do some other tests to verify whether that was happening or not, whether I was actually silolating my polyphenols. So upon the last silylation attempt that I did, we decided to try to verify that. And so what I did was I took it over to Esther, the GCMS, and I put my vial in there. And the mass spec says, yes, this is your silylated stuff, right? This blue spike is evidence of silylation. And then I took it over to Donna and I ran it through Donna, the HPLC. And what this looks like is, yes, there's some sort of silylation occurring. The bumps of the peaks have actually been flipped. And so we think that maybe there's some sort of difference occurring there because of the polarity change now of putting a silicon in there in place of an oxygen. So we're hopeful. We are hopeful. So overall, what we did this summer was we improved the method of extraction for us, for what works for us. We found an appropriate column to use for trying to determine individual polyphenol content. We found a couple mobile phases that we think are good candidates as well. And thus, we've made pretty good progress on the methodology of determining individual polyphenols within a food source. We just really need to figure out that identification component of that. So next steps, we actually have some produce that's going to be coming in. So we will be trying to see if maybe it'll be easier to do on potatoes and onions that are coming in soon. Maybe, we obviously have to continue working on figuring out the polyphenol content. So we're going to continue to do that. Maybe the Advion will be working, which is it's another mass spec machine, but it's a little different. So I can just kind of dip my rod in there and then put it straight into the machine, and it'll give me a fragmentation result. So hopefully that can work. That'll prevent us from having to silylate. We're also going to get some concentrated individual polyphenols from some literature that we read that rice should have. And there we can make some calibration curves and start to figure out retention times, and maybe we can be able to match up some spectra to some retention times of some concentrates. And then we have another method of increasing concentration. It's called solid phase microextraction, and we can use it to increase the concentration of our compounds before they go into the GCMS, and maybe that'll help us figure out exactly what these polyphenols are. Yeah, so I just wanted to say thank you to CSE Squared and CSRI for the opportunity and the funding and the lab area and equipment to use. Dr. Ott and Dr. Riles, these are my advisors. Thank you for the support and the help and everything you guys did. Thank you, Akalai, for her She's my predecessor on this project for her work that she did to get the ball rolling. Dr. Ball, Dr. Peterson, and Dr. Arpin for the assistance with the organic chemistry. Blaine in the stockroom for the assistance with, my chemical needs, and some chit chat. I want to thank Raquel for the rice and the rad lab for, allowing me to learn these other assays while I'm working on this stuff. I wanted to thank JD for teaching me or helping me learn how to change some equipment and do some maintenance on some of these GCs and HPLCs. Olivia and Daniel for the wonderful pictures of Donna. I want to thank Donna and Esther. I mean, I've been working with them all summer. They're great. Matt, Shelby, Alondra, Laney, and Eugen for sharing the lab space with me. It was a great time. Everett and Lakin, keeping me entertained as always. And Delilah, my dog, for keeping me sane during all of everything, life. Just in case anybody was curious about the mechanism of silylation, it's a nucleophilic substitution. Here we go with you know some arrow pushing, and there's the organic chemistry mechanism there.